The star closest to Earth is not calm. Proxima Centauri can unleash flares that make it thousands of times brighter than normal, blasting radiation into the space around it in violent bursts that can last only seconds. And it is only about 4.2 light years away. That is essentially next door in cosmic terms. The strange part is that Proxima is not alone in this behavior. Our nearest stellar neighbors are filled with red dwarfs, small stars whose magnetic fields can produce enormous flares and intense radiation. Barnard's star is about 6 light years away. It is older than our Sun and should be relatively quiet, yet astronomers have recorded powerful flare activity from it. Wolf 359 is roughly 7.8 light years away. During only about 3.5 days, NASA's Chandra X-ray Observatory detected 18 separate X-ray flares from the star. Then there is UV Ceti, about 8.7 light years away, a star so violently variable that it became the prototype for an entire class of flare stars. These are not distant monsters hidden on the other side of the galaxy. They are among our closest stellar neighbors, and every one of them is capable of turning an otherwise ordinary looking star into a source of intense radiation. So, why are red dwarfs so violent? Why can stars that appear small and harmless produce flares powerful enough to reshape the environments of planets around them? And if this is what our nearest neighbors are doing, why does our own sun seem so unusually calm? If this kind of content helps you unwind at night, consider subscribing. We put out new space documentaries regularly, and having you here means a lot. Let's start with the closest star of them all. A star can look almost featureless from across interstellar space, yet beneath that glowing surface, enormous forces are constantly moving through it. To understand the danger around our nearest stars, we first need to look inside one. A star is a sphere of plasma held together by gravity, with nuclear fusion powering its interior. Gravity pulls everything inward, while the energy produced by fusion pushes outward, creating a balance that can persist for billions of years. The visible surface of our Sun reaches roughly 10,000 degrees Fahrenheit. Far above it, the corona, its outer atmosphere, can reach more than 3.5 million degrees Fahrenheit. We still do not fully understand why the outer atmosphere becomes so much hotter than the surface beneath it. Inside the star, plasma is always moving. This plasma is gas heated so intensely that electrons separate from their atoms, leaving electrically charged particles free to flow. Deep within the sun, enormous currents rise toward the surface, cool, and sink again, creating a continual circulation of material. That movement matters because charged plasma generates magnetic fields. Rotation adds another ingredient, twisting and stretching those fields as the star turns. Over time, magnetic energy can accumulate in regions where the field becomes especially concentrated and complex. On the Sun, this process produces sunspots, prominences, and solar flares. A flare begins when tangled magnetic fields suddenly reorganize through a process called magnetic reconnection. The stored energy is released in a burst that can spread across radio waves, visible light, ultraviolet radiation, and X rays. We can think of magnetic reconnection as a sudden release of tension within an enormous electrical system. The energy has been building for hours, days, or even longer. Then, within moments, the configuration changes and radiation races outward through space. Our sun produces these events often enough to affect technology around Earth. Strong solar activity can interfere with radio communications, disturb navigation systems, and increase the hazards faced by satellites and astronauts. Yet the magnetic engine does not operate identically inside every star. The smallest stars take a very different path. Red dwarfs contain far less mass than the Sun, but their interiors are dominated by convection. Material can circulate through much more of the star, carrying heat and magnetic energy with it. Their compact size does not make their magnetic behavior simple. Under the right conditions, these stars can build extraordinarily powerful magnetic fields and release that energy through intense flares. That distinction is crucial. A flare is not the star suddenly becoming unstable or exploding apart. The star remains intact. What changes is the configuration of its magnetic field, and the energy released during that brief rearrangement can travel outward at the speed of light. So when we look toward a red dwarf, we are seeing only its small, dim surface. Beneath that appearance is a vast magnetic system continually generating and storing energy, with occasional moments when that energy escapes into space. 4.2 light years is close enough for Proxima Centauri to become more than a point of light. It becomes a physical presence in our stellar neighborhood, although its tiny size makes it surprisingly easy to overlook. Proxima Centauri is a red dwarf with only about 15% of the Sun's radius and roughly 12% of its mass. Its visible light is so faint that you cannot see it without a telescope from Earth. Yet beneath that modest appearance, its magnetic activity can become extraordinarily intense. The reason lies deep within the star. Proxima Centauri is fully convective, meaning hot plasma can circulate through much of its interior rather than remaining confined to separate layers. That continual movement helps sustain magnetic fields, allowing energy to accumulate and then escape through powerful eruptions. Astronomers have known about this behavior for decades. In 1951, Proxima Centauri was identified as a flare star, establishing that these sudden brightenings were part of its normal behavior. The observations were only the beginning. Modern instruments have revealed how extreme those events can become. In 2016, astronomers recorded a major flare from Proxima Centauri. Then, 3 years later, a much larger event arrived in the data. On May 1st, 2019, 9 observatories watched the star across several wavelengths at nearly the same time, giving researchers an unusually detailed view of one stellar eruption. The flare changed dramatically within seconds. In ultraviolet light, Proxima Centauri became 14,000 times brighter than its ordinary level. The increase was so rapid that the event challenged existing ideas about how energy moves through a stellar magnetic field. The observations came from instruments including the Hubble Space Telescope, the Atacama Large Millimeter Array, and the Transiting Exoplanet Survey satellite. Each instrument captured a different part of the event, allowing astronomers to trace radiation across wavelengths that reveal different physical processes. What makes the 2019 flare especially useful is its timing. The ultraviolet emission rose almost immediately, while other wavelengths responded differently, giving researchers a rare opportunity to compare the stages of the eruption. We can watch the magnetic energy become radiation, almost as though the star briefly exposes the machinery beneath its surface. The amount of energy involved was extraordinary, exceeding the strongest events recorded from our Sun by a wide margin. Yet Proxima Centauri did not lose its structure. The star remained intact, continuing its long journey around the center of the Milky Way. For us, the most important detail is where that energy goes. Proxima Centauri does not erupt into empty space. Anything orbiting close enough to receive its warmth also receives its radiation, including the planets already known to circle this remarkable star. The most important feature of Proxima b is something we cannot see directly: what remains above its surface. Discovered in 2016, Proxima b is a rocky world with a minimum mass close to Earth, orbiting inside Proxima Centauri's habitable zone. That term sounds reassuring, but it describes only distance. It tells us where liquid water could potentially exist, not whether a planet can actually keep it. Proxima b circles its star at a distance of only about 4.7 million miles. From there, the radiation environment becomes fundamentally different from Earth's. The planet receives roughly 30 times more extreme ultraviolet radiation than Earth receives from the Sun, along with about 250 times more X-ray radiation. Those numbers describe the ongoing background. Flares add sudden surges on top of it. High-energy radiation reaches the upper atmosphere first, where it interacts with atoms and molecules. Extreme ultraviolet radiation can ionize atmospheric gases, knocking electrons loose and creating charged particles that become easier to remove into space. Over long periods, that process can become atmospheric escape. Hydrogen is especially vulnerable because its low mass makes it easier for the planet's gravity to lose. But heavier elements can also be removed under sufficiently intense conditions. We can picture an atmosphere as a reservoir constantly being replenished and depleted. If stellar radiation removes material faster than geological processes can replace it, the reservoir gradually falls. Models built by researchers at the National Aeronautics and Space Administration have explored what would happen if an Earth-like atmosphere and magnetic field were placed around Proxima b. Under extreme conditions, the modeled planet could lose an amount equivalent to Earth's entire atmosphere within 100 million years. That does not prove Proxima b is barren. We have no direct measurement of its atmosphere, and we do not know whether it possesses a planetary magnetic field. The distinction matters. A magnetic field could redirect some incoming charged particles, while a thick atmosphere could absorb radiation high above the surface. Oceans, underground environments, and other natural shelters could provide additional protection. Still, the star's history creates a difficult environment. Proxima Centauri is roughly 5 billion years old, giving its planet an enormous span of time during which radiation could alter its atmosphere and surface chemistry. The 2019 superflare adds another complication. Its ultraviolet brightness increased by more than 14,000 times, with the initial burst lasting less than 10 seconds. For a nearby planet, those seconds delivered a concentrated pulse of energy into an atmosphere already exposed to an intense radiation environment. We do not know exactly what happened on Proxima b during that event. There are no cameras watching its surface, no weather station measuring its air, and no instrument currently telling us whether clouds or oceans exist there. What we have instead is physics accumulated over time, and that physics tells us the planet's location may be habitable only in the narrowest sense, while the star above it continually tests how long any atmosphere can endure. There is a statistical pattern written into the way stars erupt. The larger the flare, the less often we normally expect to see it. Astronomers call this relationship a flare frequency distribution. It is essentially a map showing how many flares a star produces at different energy levels. Small events should fill the lower end of the scale, while powerful eruptions become progressively rarer. Proxima Centauri complicates that picture. In 2025, a team led by Kiana Burton and Meredith McGregor examined roughly 50 hours of observations from the Atacama Large Millimeter Submillimeter Array. They identified 463 flares across the observations, ranging from relatively modest events to some carrying enormous amounts of energy. The striking result came from the distribution itself. At millimeter wavelengths, Proxima's flare frequency followed a much steeper pattern than astronomers had measured at optical and X-ray wavelengths. In simple terms, the star produces far more small millimeter flares than the usual model would suggest. That difference matters because we normally learn about stellar activity through visible light and higher energy radiation. Millimeter observations reveal another part of the process, allowing researchers to see activity that would otherwise disappear from the record. One flare in the 2025 study increased Proxima Centauri's millimeter brightness by roughly 1,000 times. The event lasted only seconds, yet hundreds of less dramatic eruptions appeared throughout the observing campaign. If we record only the largest storms, we may mistake the star for something that erupts occasionally. Count smaller events too, and a different picture emerges. The researchers found that the millimeter flares followed a power loss slope of about 2.9, considerably steeper than the value of roughly 2 commonly measured at optical and X-ray wavelengths. A power law describes how rapidly event frequency falls as energy increases. That result does not mean Proxima b is struck by atmosphere-destroying flares several times each week. The observations cannot establish that directly. What they show is more subtle and potentially more important. The radiation environment may contain a much larger contribution from frequent smaller flares than previous estimates allowed. Earlier observations had already shown how active Proxima Centauri can be. A separate study using the Transiting Exoplanet Survey satellite found 72 flares during roughly 50 days of monitoring, an average of about 1.5 events each day. Now we have another wavelength revealing another layer of that activity. The star is not simply punctuated by spectacular eruptions separated by long stretches of ordinary behavior. Its magnetic environment is producing events across a wide range of energies. For a nearby planet, that distinction matters greatly. Habitability depends on the long-term balance between radiation received and atmospheric protection, so thousands of smaller events can become scientifically important even when none resembles the largest flare ever recorded. Proxima Centauri is therefore difficult to understand from a handful of dramatic explosions. Its true activity emerges statistically across many observations, where the pattern itself becomes the evidence. At 6 light-years from Earth, Barnard's star carries an age that changes the meaning of every flare it produces. Astronomers estimate the red dwarf is roughly 10 billion years old, more than twice the Sun's age. Its long history should have drained much of its rotational energy, leaving a star with a slow spin and weak magnetic activity. Barnard's star rotates roughly once every 130 days. The Sun turns far faster. For decades, that slow rotation made Barnard's star a useful example of an aging red dwarf, one whose magnetic engine should have become increasingly restrained. Then, on July 17, 1998, something unexpected appeared in a telescope. William Cochrane was observing Barnard's star with the McDonald Observatory's 8.9-foot telescope while searching for signs of planets. The target was its motion, not its atmosphere. Yet the spectrum suddenly contained emission lines associated with a stellar flare. Cochrane recorded additional spectra that night. Then the observation was set aside. 4 years later, Cochrane showed the data to Diane Paulson, a graduate student at the University of Texas. Paulson recognized the event and led the analysis that revealed what had happened. The flare had produced a hot blue region reaching roughly 14,000 degrees Fahrenheit, more than twice the star's normal surface temperature. The surprise came from its source. Barnard's star was already ancient by stellar standards, and its slow rotation offered little reason to expect such a powerful eruption. Yet the event was not the end of the evidence. In 2019, the Hubble Space Telescope observed two additional ultraviolet flares from Barnard's star, along with an X-ray flare. The X-ray event released roughly 16 sextillion joules of energy, while each ultraviolet flare carried roughly 30 sextillion joules. Researchers studying these observations found that Barnard's star spends a measurable fraction of its time producing high-energy events. The observed flare activity also provides a way to estimate how much radiation a nearby planet might receive over geological timescales. That matters because Barnard's star is not a young, rapidly spinning object caught in an unusually energetic phase. Its age makes the continued activity more informative. We are seeing magnetic behavior that persists long after the period when astronomers once expected these stars to become inactive. The discovery also changed how we interpret age itself. A red dwarf can lose most of its rotational speed without completely losing its ability to generate magnetic eruptions. For you, the important detail is the timescale. Barnard's star has been evolving for billions of years, yet its magnetic field can still rearrange itself violently enough to produce a detectable flare from 6 light-years away. Its age did not erase the magnetic engine. It only changed how often that engine speaks. That makes the star a valuable test of how long magnetic activity can survive inside a small stellar body. Barnard's star changed what astronomers thought age could tell them. A star can spend billions of years slowing down and still retain a magnetic system capable of sudden eruptions. The connection between rotation and magnetic activity is real, but it is not the whole story. Faster rotation generally strengthens magnetic activity because moving plasma can generate and organize stronger magnetic fields. As a star loses rotational speed, its magnetic output usually declines. Barnard's star rotates once every 130 days. The Sun completes a rotation in roughly 25 days. That difference should matter greatly. Yet the interior of a red dwarf changes the calculation. Unlike the Sun, a fully convective red dwarf does not confine convection to an outer region. Hot plasma rises from deep within, releases energy, and sinks again through the stellar interior. That circulation continually moves electrically charged material. As it flows, it helps sustain the magnetic dynamo, the internal process that converts motion and rotation into magnetic energy. Even a slowly rotating red dwarf can therefore maintain substantial magnetic activity. Magnetic fields also have complicated structures. They can emerge through the stellar surface, become concentrated, and reconnect when their geometry changes. Magnetic reconnection releases stored energy as radiation, producing a flare that can briefly outshine the star's ordinary emission. The discovery at Barnard's star encouraged astronomers to examine older red dwarfs more carefully. Instead of treating age as a simple countdown toward magnetic inactivity, researchers began asking how interior structure, rotation, and magnetic topology interact across billions of years. That distinction matters for planets. If old red dwarfs remain capable of producing energetic flares, then their planets may experience intense radiation for far longer than earlier habitability models assumed. Barnard's star has a candidate planet designated Barnard Star B. It is a super-Earth, meaning its estimated mass is greater than Earth's, although its existence remains debated. The candidate would orbit at roughly 23 million miles from its star. At that distance, stellar radiation becomes an important part of any habitability calculation. Researchers have estimated that atmospheric loss could be substantial over geological timescales, depending on the planet's atmosphere and the physical processes operating above its surface. One study estimated that thermal atmospheric escape could remove the equivalent of 87 Earth atmospheres every billion years under certain assumptions. That number is a model, not a direct measurement, because we do not know whether the candidate planet possesses an atmosphere at all. Still, the calculation reveals why stellar age matters. A planet around an ancient red dwarf may have spent billions of years beneath a magnetic environment that never completely stopped producing energetic events. For us, Barnard's star offers a broader lesson about stellar evolution. Aging changes a star's activity, but the interior still matters. The passage of time can weaken a magnetic engine without switching it off, leaving old worlds exposed to a source of radiation that their star's age alone cannot explain. Some stars announce their activity in minutes. Wolf 359 reveals it through repetition. At 7.8 light years from Earth, this red dwarf is among our closest stellar neighbors. It is extraordinarily dim, shining at roughly 1,000th the sun's visible brightness. Yet in X-rays, its behavior tells a very different story. Astronomers first recognized Wolf 359 as a flare star in 1969. Decades later, space telescopes finally became sensitive enough to watch its high energy output directly. In 2025, Scott Wolk and his colleagues combined observations from the Chandra X-ray Observatory and the XMM Newton spacecraft. Their target was Wolf 359, and their observing window lasted only 3.5 days. During that brief interval, they detected 18 separate X-ray flares, 18 eruptions in less than 4 days. For a star this active, the number is more useful than any single spectacular event. Each flare becomes another point in a statistical record, helping astronomers estimate what a planet around Wolf 359 might experience over much longer periods. The observations revealed something else. Wolf 359 produces a persistent stream of high-energy radiation even between major flares. X-rays and extreme ultraviolet radiation continually reach the region where any nearby planets would orbit. Because Wolf 359 is so dim, its habitable zone lies extremely close to the star. A planet there would need to remain near its host to receive enough energy for liquid water to potentially exist on its surface. That proximity changes the calculation. The same star that provides warmth also supplies intense radiation, and the 18 observed flares represent only the events captured during a small slice of time. From those observations, the researchers modeled how radiation could affect possible planetary atmospheres. Their results showed that an Earth-like planet in the middle of Wolf 359's habitable zone could retain an atmosphere for almost 2 billion years if it began with substantial greenhouse gases. Move inward, and the outlook changes dramatically. One candidate planet, if it exists, would receive enough X-ray and extreme ultraviolet radiation to lose its atmosphere in roughly 1 million years. That timescale is astonishingly short beside Earth's history. Multicellular life on our planet required billions of years to emerge. A world losing its atmosphere after only 1 million years would have far less time for complex surface ecosystems to develop. The outer edge offers more possibility. There, a thick atmosphere containing greenhouse gases could provide enough insulation and shielding for an atmosphere to survive much longer, potentially indefinitely under the model's assumptions. We are therefore looking at a narrow balance between warmth and radiation. A planet must remain close enough to receive energy, yet far enough away to avoid losing its atmosphere too quickly. Wolf 359 shows how that balance can shift from one orbit to another. Its flares are brief, but their significance accumulates across geological time, turning 3.5 days of observations into a glimpse of an environment that may persist for billions of years. For most stars, a flare is an event. For UV Ceti, it is part of the rhythm. The system lies 8.7 light years from Earth, within the constellation Cetus. Two red dwarfs circle one another, their changing separation tracing an elongated orbit over roughly 26.5 years. One of them carries a remarkable distinction. Its name became a category, UV Ceti, also known as Luton 726-8b, is the smaller member of the pair. Astronomers use its name for an entire class of violently eruptive red dwarfs called UV Ceti variables. The reason began in September of 1948. At Mount Wilson Observatory, astronomers watched the star brighten by more than 4 magnitudes. The increase unfolded within minutes, then gradually faded during the following day. During that eruption, the star's surface reached temperatures above 18,000 degrees Fahrenheit. That was only the beginning. Later observations showed UV Ceti increasing its total brightness by a factor of 100 within seconds. The strongest recorded events have produced increases approaching 1,000 times its normal brightness. You can think of ordinary stellar brightness as a baseline. UV Ceti repeatedly tears away from that baseline, then settles back toward it. Its rotation helps explain why. UV Ceti completes one rotation in only about 4.8 hours. That rapid spin drives an exceptionally powerful magnetic dynamo, the process that converts the motion of conducting plasma into organized magnetic fields. Those fields are continually stressed by the star's internal motion. Small magnetic eruptions can occur again and again. Between larger events, the star can remain active enough that its high energy output never truly settles into a long, inactive interval. Then the major flares arrive. A powerful eruption can release around 10 to the 27th power joules of energy. Written out, that means a 1 followed by 27 zeros. For a nearby planet, the danger would extend beyond a single flash of radiation. Repeated eruptions could alter an atmosphere, drive particles into the upper layers, and expose the surface to increasingly harsh conditions. The system creates another complication. Both red dwarfs flare. Any planet orbiting one of them would therefore exist within a stellar environment shaped by two active magnetic sources. Their radiation would arrive from different directions as the binary stars move through their orbit. Yet, distance makes UV Ceti unusually valuable to science. At less than 9 light-years away, astronomers can study individual eruptions with instruments powerful enough to separate different forms of radiation. We can measure their timing, energy, temperature, and evolution. Each observation adds another piece to our understanding of stellar magnetic activity. UV Ceti therefore serves as more than an extreme example. Its name has become shorthand for a particular kind of stellar behavior, one where magnetic energy can accumulate rapidly and escape with astonishing force. For astronomers studying the environments around red dwarfs, that makes this nearby binary system an important natural laboratory where stellar physics becomes visible through repeated bursts of energy. The key to a red dwarf's behavior lies beneath its surface, where heat and motion never settle into a simple pattern. Deep inside, plasma rises, cools, and sinks again. Because plasma carries electric charge, its movement generates magnetic fields throughout the star. Those fields are woven through circulating material, connecting regions that constantly shift. Rotation adds another layer of complexity. A red dwarf does not turn as a perfectly rigid sphere, with every region moving at exactly the same rate. Different zones can rotate differently, stretching and twisting magnetic field lines as the star turns. That twisting stores energy inside the magnetic field. You can picture a rubber band being wound tighter and tighter. The tension grows with every turn. Eventually, the stored energy has to escape. In a stellar flare, magnetic field lines suddenly reconnect. Reconnection is the process in which tangled magnetic fields change their arrangement and rapidly form a new one. The change releases stored magnetic energy as radiation and accelerated particles. For a star like the Sun, the interior is organized into distinct regions. Heat moves through those layers by different processes, and their boundaries influence how material circulates and how magnetic fields develop. Red dwarfs follow a different internal design. A fully convective red dwarf has no broad radiative zone separating its core from its outer layers. Material can circulate through much of the entire stellar interior. The result is a magnetic environment that remains deeply connected to the star's internal motion. This matters because magnetic activity does not simply switch off when the star grows old. Barnard's star demonstrates the point. Its rotation has slowed dramatically with age, yet observations still reveal ultraviolet and X-ray flares. Age changes the star's behavior, but it does not erase the magnetic engine operating within it. Proxima Centauri shows another side of the same physics. Its activity reflects a more rapidly changing magnetic environment, where energy can accumulate and erupt with extraordinary frequency. Different stars can therefore produce different flare patterns while sharing the same fundamental mechanism. For astronomers, that connection is important. When we study a flare, we are seeing the surface expression of processes occurring deep inside a star, processes we cannot observe directly. The radiation gives us an indirect view. We can measure when an eruption begins, how quickly its brightness changes, and which wavelengths carry its energy. Those observations allow researchers to reconstruct pieces of the magnetic activity hidden beneath the stellar surface. A star's appearance tells us relatively little about the machinery beneath it. Two red dwarfs may look similarly dim from Earth, yet their magnetic behavior can differ dramatically. Rotation, internal circulation, age, and magnetic geometry all shape the eruptions we eventually observe. So, the violence of these stars is written into their structure. Their flares emerge from a magnetic system continuously stirred by the star itself. And that makes habitability much more complicated. A planet does not simply orbit a star. It exists inside the magnetic environment that star creates. The first damage from a stellar flare can begin far above any surface, where the atmosphere meets incoming radiation. When an eruption reaches a planet, its energy arrives across many wavelengths. Radio waves and visible light are part of the event, yet ultraviolet radiation and X-rays carry enough energy to alter atmospheric chemistry directly. The first reactions unfold in the upper atmosphere. High-energy particles collide with molecules there, creating reactive compounds that can interfere with ozone formation and survival. Ozone is especially important because it absorbs much of the ultraviolet radiation that would otherwise reach the ground. Once that shield weakens, the surface receives a larger dose of ultraviolet light. The chemistry can become self-reinforcing. More ultraviolet radiation reaches exposed molecules. More molecules break apart. More chemical reactions follow. A flare may last only minutes or hours, while the atmospheric changes it triggers can persist much longer. A 2025 atmospheric modeling study examined this problem under sustained flare conditions. In the most active scenarios, as much as 80% of a planet's stratospheric ozone could disappear within 8 years. That number describes a modeled outcome rather than a universal fate. The result depends on atmospheric composition, pressure, magnetic protection, stellar activity, and the planet's distance from its star. Still, the chemistry has a direct consequence. Ultraviolet radiation can damage complex organic molecules. On Earth, nucleic acids carry genetic information inside living cells. Sustained exposure can break these molecules apart faster than exposed organisms can repair the damage. A planet does not need to lose every trace of its atmosphere to become difficult for surface life. There is another process at work. Charged particles from stellar eruptions can strike the upper atmosphere and transfer momentum to atmospheric molecules. Some particles receive enough energy to escape the planet's gravitational pull. This process is called atmospheric sputtering. Over geological timescales, repeated particle bombardment can gradually remove atmospheric material into space. The loss may be slow during any individual event, yet billions of years provide an enormous amount of time for small effects to accumulate. Magnetic fields can reduce some of this erosion by deflecting charged particles away from the atmosphere. A thick atmosphere can provide another layer of protection, while ozone absorbs dangerous ultraviolet radiation before it reaches the ground. Earth benefits from all three. Around an active red dwarf, the balance can be very different. A planet may begin with an atmosphere and still lose part of it through repeated stellar activity. Its chemistry may change first, while physical erosion gradually follows. You can think of the atmosphere as both a shield and a reservoir. Radiation attacks the chemistry, particles attack the upper layers, and time connects the two processes. For a planet orbiting a violent star, habitability therefore becomes a moving target. The question is no longer simply whether liquid water could exist. We also have to ask whether the planet can keep the atmosphere that allows complex chemistry to continue. The habitable zone around a red dwarf is a remarkably narrow neighborhood, and it comes with an unusual gravitational price. Because these stars emit far less energy than the Sun, a planet must orbit much closer to receive enough warmth. Proxima b circles Proxima Centauri at roughly 4.7 million miles, placing it extraordinarily close to its star. At that distance, gravity has had billions of years to reshape the planet's rotation. The effect is called tidal locking. A planet becomes tidally locked when its rotation period matches the time required to complete one orbit. The same basic process has locked our moon to Earth. One hemisphere continually faces the star. The opposite hemisphere faces away. That does not automatically create one boiling side and one frozen side. The atmosphere matters enormously. If a planet has enough air, winds can carry heat from the illuminated hemisphere toward the darker one, reducing the temperature difference between them. But the climate would still be unlike Earth's. The star would remain fixed in the same region of the sky, while the opposite hemisphere would never receive direct starlight. Between them lies the terminator, the moving boundary between day and night on an ordinary, rotating world. On a tidally locked planet, that boundary can become a region of particular interest. If the atmosphere is thick enough, winds may transport heat across the planet. Ocean currents could redistribute energy as well. Clouds might reflect some incoming radiation while also trapping heat. A planet with a sufficiently dense atmosphere could therefore avoid the simplest picture of one side burning while the other freezes. Still, proximity creates another problem. The same closeness that provides enough stellar energy also places the planet deep inside the star's radiation environment. Proxima b receives substantially more high-energy radiation than Earth does from the Sun, while its atmosphere must remain close enough to the star to maintain temperatures suitable for surface liquid water. The geometry matters. Radiation spreads outward as it travels away from a star. If the distance is reduced by a factor of 20, the same energy is concentrated over an area roughly 400 times smaller. That is the inverse square law. So, moving a planet inward does not simply make its star appear somewhat brighter. The energy received at the planet rises dramatically. For red dwarf planets, this creates a difficult balance. A world farther away receives less radiation and may become too cold for surface liquid water. A world close enough to remain warm can face stronger stellar irradiation and tidal effects. There is another subtle consequence of tidal locking. The planet's magnetic environment can evolve differently as its rotation slows, potentially affecting how effectively it interacts with charged particles from the star. Scientists still debate how these factors combine. Atmospheric thickness, ocean coverage, cloud formation, magnetic protection, planetary composition, and stellar activity can all change the outcome. No single feature determines whether a tidally locked world is habitable. You might imagine habitability as a simple distance from a star. Around red dwarfs, it is much more complicated. The potentially temperate region sits close to a star whose radiation can be intense, while gravity can permanently synchronize the planet's rotation. The same neighborhood that offers warmth also exposes a world to conditions that Earth never experiences. Earth has preserved stranger evidence of stellar violence than we might expect. Deep beneath the ocean floor, scientists have found atoms that arrived from beyond our solar system. One of the most important is iron 60, a radioactive isotope associated with massive stars and their explosive deaths. Its presence in terrestrial sediments provides a rare geological fingerprint of nearby stellar events. But the timing matters. The strongest evidence places these deposits far later than the Devonian extinction. Studies of deep-sea sediments and crusts have detected iron 60 dating to roughly 2 million years ago, with additional material arriving across several million years. Researchers have linked these deposits to one or more supernovae that occurred within a few hundred light-years of Earth. We can actually trace that material, dust, carrying freshly produced radioactive atoms, drifted through interstellar space before reaching our solar system. Some of those particles entered Earth's environment, eventually settling into sediments where they remained long enough to be detected. The Devonian story is different. Around 359 million years ago, the late Devonian extinction marked a major collapse in biodiversity. Scientists have proposed several explanations, including volcanic activity, climate change, and changes in ocean chemistry. A nearby supernova has also been proposed as a possible contributor. The idea has a physical basis. A sufficiently close supernova could increase cosmic radiation around Earth for an extended period. Those energetic particles could alter atmospheric chemistry, damage the ozone layer, and allow more ultraviolet radiation to reach the surface. Yet there is an important distinction. Iron 60 has not established a supernova cause for the Devonian extinction. In fact, the leading supernova hypothesis proposed looking for other long-lived radioactive isotopes within Devonian extinction layers as a decisive test. That uncertainty makes the evidence more interesting, not less. We already know that stars can leave physical traces on Earth long after their light has passed. The ocean floor can preserve material from explosions that occurred millions of years ago, allowing us to reconstruct events no human ever witnessed. and the distances involved are surprisingly modest by galactic standards. Modeling of the Iron 60 deposits suggests some of those supernovae occurred roughly 200 to 400 light years away. That is far enough to spare Earth's surface from immediate devastation, yet close enough for stellar debris to reach us. For our planet, the atmosphere remains a powerful shield against much of the radiation produced by distant stellar explosions. Even so, the geological record shows that Earth exists inside a neighborhood where stars have died close enough to leave fingerprints. We are not isolated from the lives of other stars. Their explosions can cross interstellar space, enter our atmosphere, and become part of the ground beneath our feet. The evidence is small, measured atom by atom, but the distances behind it are immense. Distance becomes dangerous in a surprisingly precise way. For a supernova, astronomers estimate that an explosion within roughly 30 light years could severely damage Earth's ozone layer, allowing much greater ultraviolet radiation to reach the surface. That threshold is an estimate, shaped by the star's energy output, the explosion's direction, and Earth's atmospheric condition at the time. Even so, the scale gives us something tangible to work with. 30 light years. Our nearest known supernova candidates are much farther away. Spica, a massive star system, often discussed in this context, lies roughly 250 light years from Earth. Its eventual explosion would be spectacular, but the distance greatly reduces its biological danger. For us, that difference matters. A supernova hundreds of light years away can still send particles across interstellar space. Yet the radiation intensity falls rapidly with distance, spreading over an ever larger sphere as it travels outward. By the time the wave reaches Earth, much of its destructive potential has been diluted. A planet orbiting a flare star faces a different geometry entirely. Its star is directly overhead. The dangerous radiation does not cross hundreds of light years before arriving. It travels across a planetary system only a few million miles wide, reaching the planet moments later. That changes the meaning of a stellar kill zone. Around a supernova, the dangerous region can be measured in light years. Around a highly active red dwarf, the vulnerable region is often measured in millions of miles. And the planet itself may already occupy that space. Consider Proxima b. Its orbit places it only a few million miles from Proxima Centauri, because the star emits far less visible energy than the Sun. That close orbit is necessary to receive enough warmth for the planet to remain within the star's habitable zone. But every flare begins from that same nearby source. There is no distant safe orbit hidden within the habitable zone. Moving outward reduces the radiation exposure, yet it also reduces the stellar energy available to keep the surface warm. Moving inward improves the energy supply while increasing the intensity of every eruption. The geometry leaves little room. You can see why habitability around red dwarfs is such a difficult calculation. Astronomers must consider the star's brightness, flare frequency, radiation spectrum, atmospheric chemistry, magnetic protection, and the planet's orbital distance at the same time. One variable cannot tell the whole story. Earth benefits from an unusual arrangement. Our sun is stable enough to support a long-lived atmosphere, while our planet orbits far enough away that ordinary solar activity does not repeatedly overwhelm it. For a planet around a flare star, those conditions may never align. The danger, therefore, has two very different scales. A nearby supernova can threaten worlds across dozens of light years. A flare star can threaten its own planet from only millions of miles away. In one case, danger arrives from across the galaxy. In the other, The planet lives beside the source. There is a strange imbalance hidden in the numbers. The stars we have been studying are unusual in their behavior, yet they are ordinary in another, much larger sense. Red dwarfs are the most common stars in the Milky Way. They account for roughly three-quarters of the galaxy's stellar population, with some estimates placing their share closer to 85%. That changes the question entirely. If our galaxy contains roughly 200 billion stars, then well over 100 billion may be red dwarfs. Some estimates place the total closer to 250 billion, which would mean roughly 187 billion to 212 billion red dwarfs. And planets appear to be common around them. Astronomers have estimated that roughly 40% of red dwarfs could host a rocky planet near the star's habitable zone. If that estimate holds, the resulting population could number in the tens of billions across the Milky Way. That is an extraordinary possibility. The galaxy may contain billions upon billions of rocky worlds receiving enough energy for liquid water. Many could have sizes comparable to Earth. Many could occupy orbital regions where temperatures appear suitable for familiar chemistry. Yet the stars illuminating those worlds are frequently active. This creates a problem that cannot be solved by counting planets alone. A world can sit inside a mathematically defined habitable zone while its atmosphere is repeatedly altered by stellar radiation. The term habitable zone describes an orbital region where surface conditions could potentially allow liquid water. It does not guarantee oceans, breathable air, stable climates, or life. That distinction matters enormously. For decades, the search for potentially habitable planets often emphasized distance from the star. Find the right temperature range, then investigate the world itself. Red dwarfs complicated that picture. Their habitable zones lie close to the stellar surface, placing planets within reach of intense magnetic activity. Their long lifetimes also give those planets enormous amounts of time to experience whatever environment their stars create. A planet might endure, or its atmosphere might gradually disappear. Across our nearby stellar neighborhood, we have encountered the same basic category repeatedly. Proxima Centauri is a red dwarf. Barnard's star is a red dwarf. Wolf 359 is a red dwarf. UV Ceti belongs to the same class. They differ greatly in age, rotation, and flare behavior. Yet each has shown that red dwarfs can remain magnetically active in ways that challenge simple expectations. And this is where the numbers become difficult to ignore. The galaxy's most numerous stars are also the stars whose planetary environments may be most strongly shaped by stellar activity. We are left with a cosmic paradox. The worlds may be abundant, the chemistry may be possible, the water may exist, but surrounding them are stars capable of reshaping their atmospheres over immense stretches of time. If red dwarfs truly dominate the population of potentially habitable planets, then understanding their violence is no longer a side question in the search for life. It becomes one of the central questions. For most of cosmic history, the sun has been doing something remarkably ordinary. It has simply remained stable enough for a planet to keep changing around it. The Sun belongs to the G-type main sequence class, a category representing only a small fraction of the stars in the Milky Way. Most stars are smaller and cooler red dwarfs, while the Sun occupies a comparatively uncommon middle ground. Its activity is real. Solar flares can release enormous amounts of energy, disrupting radio communications and affecting satellites near Earth. Powerful eruptions can also drive streams of charged particles toward our planet, producing geomagnetic storms and brilliant auroras. Yet, the Sun has an important difference. Its interior is divided into distinct regions. Deep inside, energy moves outward through radiation before reaching a convective layer closer to the surface, where hot plasma rises and cooler material sinks. That structure changes how the magnetic field develops. The sun still twists magnetic fields and stores enormous amounts of energy. When those fields rearrange, flares and coronal mass ejections can erupt from the surface. But its magnetic engine operates within a layered interior. Red dwarfs are different. Their interiors can remain fully convective, allowing material to circulate from deep within the star toward its surface. That creates a very different environment for generating and maintaining magnetic fields. Rotation matters as well. The Sun takes roughly 25 days to complete one rotation near its equator, with higher latitudes rotating more slowly. Its magnetic cycle therefore builds and reorganizes over years rather than producing the relentless activity seen from the most extreme flare stars. Earth also occupies a fortunate orbital position. Our planet circles the Sun at roughly 93 million miles. By the time solar radiation reaches us, it has spread across an enormous volume of space, reducing the intensity reaching each square mile. Distance alone does not protect Earth. Our planet also has a global magnetic field that deflects many charged particles, while its atmosphere absorbs much of the incoming ultraviolet and X-ray radiation. Those protections developed within a long-lived planetary environment. Life, therefore, inherited several advantages at once. A moderately active star provided energy, a distant orbit moderated that energy, and Earth's atmosphere and magnetic field helped shield the surface. We should be careful with the word rare. Astronomers cannot yet say that the Sun is uniquely suited to life, because we have examined only a tiny fraction of all planetary systems. We also do not know how frequently life emerges or survives around different kinds of stars. Still, our local stellar census offers an important perspective. The Sun is not the dominant type of star in our galaxy. Red dwarfs are, and many of those stars remain magnetically active for immense spans of time. Their planets may therefore experience environments very different from the one Earth has known. When we look back at our own star, its greatest distinction may be its restraint. The Sun can flare, erupt, and disturb our technology, yet it has provided Earth with a remarkably durable source of energy. For billions of years, that stability gave us small planet time. Life has already shown us that survival can take unexpected forms. On Earth, organisms endure conditions once considered impossible, from acidic waters to deep ocean vents, where chemistry replaces sunlight as the source of energy. That resilience leaves a narrow possibility around red dwarfs. A planet does not necessarily need a perfectly gentle star to remain biologically active. What matters is whether its atmosphere can absorb, redistribute, and recover from repeated disturbances over long periods of time. A thick atmosphere could provide one layer of protection. Carbon dioxide absorbs infrared radiation and can contribute to atmospheric warming, while deeper atmospheric layers can absorb much of the high-energy radiation arriving from above. There is another possibility. The timing of stellar activity may matter enormously. Young red dwarfs are generally much more active than older ones. During roughly the first 40 million to 100 million years of a red dwarf's life, powerful flares can occur far more frequently than they do later. That creates a difficult beginning. A newly formed planet could spend its earliest geological ages beneath intense stellar bombardment, while its atmosphere is still developing and its surface is undergoing major chemical changes. If enough atmosphere survives, however, the environment around the star can evolve as the star itself ages. The change is gradual. Astronomers have been studying this progression through the habitable zones and M-dwarf activity across time program, designed to measure how red dwarf activity changes with stellar age. Observations from the Hubble Space Telescope showed that young red dwarfs can produce flares hundreds of times more energetic than those from middle-aged examples. That difference matters. A planet that would struggle beneath the radiation of a young star might experience a very different environment billions of years later. The atmosphere could also respond over time, rebuilding some chemical compounds after individual eruptions and redistributing energy through winds and circulation. You can think of the planet as part of an evolving system. Its star changes, its atmosphere changes, its surface changes. Any life that emerges would exist within all three processes at once. Earth gives us another reason to remain cautious about simple predictions. Life has repeatedly occupied environments where temperature, pressure, acidity, radiation, or chemistry would challenge familiar organisms. That does not prove life can survive around a violent red dwarf. It only tells us that biology has room to surprise us. Perhaps organisms around these stars would remain beneath protective layers of soil, ice, or water. Perhaps an atmosphere thick enough to absorb much of the incoming radiation could allow complex chemistry near the surface. Another possibility is that life could adapt to cycles of stellar activity, becoming active during longer intervals of reduced radiation. Each possibility carries conditions we have not yet tested directly. The central uncertainty is therefore larger than whether red dwarfs flare. We know they do. What remains unknown is how planets respond over geological timescales and whether biology can exploit the environments that survive. For now, the evidence leaves the door open. The galaxy's most common stars may offer some of its most difficult homes for life, yet difficulty alone is not a verdict. We have only one confirmed living world as our reference point, and one world is a very small sample from which to judge an entire galaxy. Proxima b is where our assumptions meet their limits. We can measure its orbit, estimate its mass, and calculate the radiation reaching it, yet the planet itself remains almost entirely beyond direct inspection. Its orbit carries it around Proxima Centauri every 11.2 days, at roughly 4.7 million miles from the star. That distance places it within the region where liquid water could potentially exist, despite receiving vastly different conditions from Earth. The radiation environment is especially difficult. Even outside major flares, Proxima b receives about 30 times Earth's extreme ultraviolet radiation and 250 times its X-ray radiation. Those numbers describe the ongoing background before the star erupts again. Then the flares arrive. For minutes or hours, the high-energy environment can rise dramatically, adding intense radiation and charged particles to an atmosphere already exposed to an active red dwarf. Models show that atmospheric escape could become substantial under these conditions, especially when the upper atmosphere expands from heating. Yet, there is a crucial gap between modeling and observation. We do not know whether Proxima b possesses a magnetic field. A planetary magnetic field could reduce some forms of atmospheric loss by deflecting charged particles, although it would not provide perfect protection. Current observations cannot measure such a field directly at this distance. The atmosphere itself presents an even larger mystery. Proxima b does not regularly pass between us and its star from our viewing angle, so astronomers cannot use the usual transit method to sample starlight filtered through its atmosphere. Instead, researchers must infer possibilities through models, orbital measurements, and the behavior of its host star. That leaves us with an unusual kind of planetary portrait. We know the world exists. We know its minimum mass is roughly 1.3 times Earth's mass, and we know its orbit with remarkable precision, but its surface remains hidden from direct examination. Perhaps an atmosphere survived the star's energetic youth. Perhaps water remains beneath clouds, ice, or a deeper atmospheric layer. A sufficiently strong magnetic environment could alter the balance again. Or the planet may have lost much of what once surrounded it. Some models have found that an Earth like atmosphere could be removed over geological timescales under especially severe conditions, while other studies emphasize how strongly the outcome depends on magnetic protection, atmospheric composition, and the history of the planet itself. So when we call Proxima b potentially habitable, the word potentially carries most of the weight. The planet sits in the right orbital region. Its environment remains uncertain, and that uncertainty is not an embarrassment for astronomy. It is the boundary of what our instruments can presently reveal. Weather on Earth changes from hour to hour, but stellar weather operates on a vastly different scale. Around a red dwarf, the atmosphere of space itself can become an ever-changing environment shaped by magnetic eruptions, energetic particles, and bursts of radiation. Astronomers use the term stellar weather to describe this activity. When its effects spread through surrounding space, we often call it space weather. The idea is familiar, even if the forces are not. A star has periods of greater activity, changing magnetic conditions, and eruptions that can alter everything nearby. Our Sun provides the clearest example. Its magnetic activity follows an approximately 11-year cycle, rising toward a period called solar maximum before declining again. During the strongest phases, solar flares and other eruptions can interfere with satellites, radio communications, and electrical systems on Earth. Red dwarfs behave differently. Their activity does not settle into such a dependable rhythm. Large flares can appear with little warning, and the intervals between major events can vary dramatically. Some eruptions arrive only hours apart. Others may be separated by weeks. That unpredictability changes the problem for any nearby planet. Imagine trying to understand an atmosphere when its star can suddenly increase its high energy output without an obvious schedule. The planet cannot prepare for a storm that has no reliable season. Research on Proxima Centauri has revealed another complication. Astronomers studying its flare behavior have found that powerful events occur more frequently than some conventional statistical models would predict. The distinction matters. A model can describe an average rate of stellar activity, yet averages do not tell us when the largest eruption will occur. For a planet exposed to repeated radiation, timing can become as important as total energy. One enormous flare, arriving after an atmosphere has partially recovered, could produce a different result from several eruptions arriving close together. Atmospheric chemistry has time-dependent responses, and repeated disturbances may prevent protective compounds from rebuilding completely. The same principle applies to planetary magnetic fields. A magnetic field can deflect some charged particles, but its effectiveness depends on its strength, the incoming particle energy, and the structure of the surrounding stellar wind. During intense stellar activity, those conditions can change rapidly. So, the environment around a red dwarf is never simply a fixed radiation level. It is dynamic. For a planet in the habitable zone, the star's behavior becomes part of the planet's climate system. High energy radiation can alter atmospheric chemistry. Energetic particles can drive atmospheric escape, and stellar outbursts can repeatedly disturb conditions at the surface. On Earth, we design systems around the possibility of severe weather. We track hurricanes, measure atmospheric pressure, and watch storms develop across the oceans. A planet orbiting a violent red dwarf would face a different challenge. There may be no dependable forecast. The surrounding space could remain active for millions or billions of years, with powerful eruptions arriving according to patterns we still struggle to predict. Life, if it existed there, would have to persist within that changing environment rather than simply endure an occasional, exceptional storm. And that makes stellar weather more than a description of a star's behavior. It becomes part of the environment in which an entire planet must exist. In 1950, Enrico Fermi was sitting at lunch at Los Alamos when a simple question entered the conversation. If intelligent life is common across the galaxy, where is everybody? The question became known as the Fermi paradox. It remains unresolved. Our galaxy is ancient. The Milky Way has existed for more than 13 billion years, while the Sun formed much later, roughly 4.5 billion years ago. Countless stars are older than ours, giving any civilizations around them enormous stretches of time to develop technology and spread beyond their original worlds. Even using spacecraft far slower than the speed of light, a civilization with a substantial head start could potentially cross enormous regions of the galaxy over millions of years. Yet, we have found no confirmed visitors. No unmistakable transmissions have been received. No artificial structures have been identified beyond reasonable doubt. No technological civilization has announced itself across the stars. There are countless possible explanations. Perhaps intelligent civilizations rarely develop. Perhaps technological societies destroy themselves before spreading very far. Maybe interstellar travel is vastly more difficult than we imagine, or advanced civilizations choose to remain hidden. Red dwarfs introduce another possibility. If most stars are red dwarfs, then most planetary systems may spend their histories beneath conditions very different from those on Earth. Their planets can orbit close to their stars, where radiation and stellar activity become persistent parts of the environment. That does not prevent life completely. Simple organisms could potentially survive where complex ecosystems struggle. Life might remain beneath oceans, under rock, or inside environments shielded from the worst stellar radiation. But the path from basic chemistry to complex organisms requires immense stretches of biological and environmental stability. That distinction matters. A planet might support life without ever producing forests, animals, civilizations, or anything capable of building a radio transmitter. The galaxy could therefore contain countless living worlds while remaining almost completely undetectable to us. This idea connects with the rare Earth hypothesis, which proposes that complex life may require an unusually precise combination of conditions: a suitable star, a stable planetary orbit, long-term atmospheric protection, and billions of years without catastrophic disruption could form a narrow chain of requirements. Our Sun happens to satisfy that chain. It is a G-type star, neither exceptionally massive nor exceptionally small. Earth orbits at a distance that allows liquid water to persist across enormous spans of time. Its atmosphere and magnetic field provide additional protection, while the planet itself has remained geologically active for billions of years. None of these conditions guarantees intelligence. Together, however, they create an environment in which intelligence had time to emerge. That may be the deeper connection to the Fermi paradox. The galaxy does not need to be empty for us to see no one. It only needs complex life to be rare enough that technological civilizations appear extraordinarily far apart in space and time. Perhaps the universe is full of living worlds that never become technological. Perhaps civilizations are common, but their windows of communication are brief. Or perhaps the conditions that allowed us to look outward are themselves unusual. If so, our sun's relative stability is more than a pleasant feature of home. It may be one of the rare circumstances that allowed a species to survive long enough to ask why the stars seem empty. Some of the most important discoveries in astronomy begin with a missing measurement. For Proxima b, that missing measurement is its atmosphere. We know the planet's mass and orbit, yet no telescope has directly shown us what surrounds its surface. We do not know whether it has a magnetic field. That matters because a magnetic field could deflect some charged particles from the host star, reducing the erosion of the upper atmosphere. Without one, atmospheric loss could become much more significant over geological time. Then there is the surface itself. We have no direct image of its terrain, no map of its continents or oceans, no measurement confirming liquid water. Even the planet's rotation remains uncertain, although its close orbit makes tidal locking a strong possibility. Our knowledge of the star is incomplete too. Proxima Centauri has been observed repeatedly, but stellar activity varies over time. A handful of observing campaigns cannot capture every flare across decades. For nearby red dwarfs, we often build a picture from separate windows rather than continuous records. Wolf 359 illustrates the problem. Astronomers have monitored its activity during limited observing periods, revealing powerful flares that tell us something about its behavior. Yet those observations cannot establish exactly how often the largest events occur across the star's entire lifetime. Barnard's star offers another piece of the puzzle. Its activity appears weaker than some neighboring red dwarfs, but even there, our measurements sample only particular moments. Stellar weather can change between observations, leaving large portions of the story unrecorded. Life presents an even deeper uncertainty. We know terrestrial organisms can survive intense conditions, including radiation and extreme environments. What we do not know is whether the chemistry required for complex life could remain stable beneath the long-term radiation environment of a flare-active red dwarf. Could an atmosphere and ocean redistribute enough energy to soften the extremes created by tidal locking? We do not yet have the observations needed to answer that. The search for biosignatures faces another obstacle. A biosignature is a chemical pattern in an atmosphere that could indicate biological activity, although natural processes can sometimes produce similar signals. The James Webb Space Telescope has begun studying atmospheres around some small exoplanets, but Proxima b presents a difficult target. It does not pass directly in front of Proxima Centauri from our viewpoint, so we cannot use repeated transits to analyze its atmosphere in the easiest way. Instead, researchers must extract information indirectly, separating the faint planetary signal from the much brighter star. That distinction is important. An absence of evidence is not evidence of a barren world. It simply marks the boundary between what our instruments can measure and what remains beyond them. You can see that boundary in almost every question surrounding these planets. We know enough to calculate possibilities, model atmospheric loss, estimate radiation, and test competing scenarios. We do not yet know which scenario nature chose. That uncertainty is not a weakness in the search for life. It is the reason the search continues, because every improved observation turns one unanswered question into something measurable. The next generation of telescopes will change what we can ask of these distant worlds. For now, much of our knowledge comes indirectly. We measure a star's motion, its brightness, and the faint influence of planets orbiting nearby. Soon, instruments will begin separating the light of those planets from the stars that overwhelm them. The James Webb Space Telescope is already doing part of this work. Around the red dwarf star TRAPPIST-1, 7 rocky planets follow compact orbits. Their combined system offers astronomers an unusual laboratory for studying worlds exposed to intense stellar activity. By analyzing starlight filtered through their atmospheres, researchers can search for gases that reveal what remains above their surfaces. That evidence matters. An atmosphere leaves chemical fingerprints. Different gases absorb different wavelengths of light. When those patterns appear in a spectrum, we can begin reconstructing the composition of a world we cannot directly visit. The extremely large telescope in Chile will push this technique further. Its primary mirror will measure roughly 128 feet across, giving it extraordinary light-gathering power and sharpness. For Proxima b, that capability could become especially important. The planet is close enough to Earth to remain one of our most compelling targets, yet its parent star is vastly brighter. Separating the planet's faint signal from that stellar glare requires instruments capable of extraordinary precision. If astronomers can isolate that signal, they could search for atmospheric molecules and examine how the planet interacts with its star. That would tell us something no model can provide alone. What actually survived? Beyond these instruments, NASA is developing concepts for the Habitable Worlds Observatory, designed around a different goal. Rather than studying only planets around red dwarfs, it would directly image Earth-like worlds around nearby sun-like stars and search their atmospheres for possible biosignatures. The Alpha Centauri system is especially interesting because 2 of its stars resemble our Sun more closely than Proxima Centauri does. At roughly 4.5 light-years away, they are among the nearest targets available for future searches. Radio astronomy offers another path. Magnetic fields can produce signatures that travel across space. Detecting those signals from exoplanets could help reveal whether a planet possesses one of the protections we have repeatedly found difficult to measure. Each new instrument, therefore, answers a different part of the same problem. Atmosphere, magnetism, chemistry, stellar activity. Together, those measurements could turn speculation into evidence. The timescale is important too. Some of these observatories are already operating, while others are being built, designed, or studied for future missions. The most revealing observations may arrive within the next decade or two. For you, that means the question is changing in a subtle way. We are moving from asking what these planets might be like to measuring what they actually contain. And once the instruments become sensitive enough, even a world 4 light-years away may begin giving us details that today exist only inside computer models. The distance remains enormous. Our ability to investigate it is finally catching up. The nearest stellar neighborhood contains a useful exception to everything we have been examining. Alpha Centauri is a system of 3 stars, bound together by gravity. Proxima Centauri is the closest member to Earth, while Alpha Centauri A and Alpha Centauri B form a separate pair farther out. The 2 larger stars are remarkably familiar. Alpha Centauri A is a G-type star, broadly similar to our Sun. Alpha Centauri B is slightly cooler, belonging to the K-type class. Together, they follow long elliptical orbits around their shared center of mass, their separation changing substantially over an 80-year cycle. Their environment is different from Proxima's. Neither star is known for the relentless flare behavior associated with the most active red dwarfs. Their magnetic activity can still produce flares, ultraviolet radiation, and streams of charged particles, but the overall pattern is less extreme. For a planet nearby, that distinction could matter enormously. A world does not need perfect conditions. It needs enough stability for chemistry to persist, atmospheres to survive, and biological systems to develop over immense spans of time. The difference between occasional stellar disturbance and persistent bombardment could shape that entire evolutionary path. Yet, we still do not know whether Alpha Centauri A or Alpha Centauri B possesses an Earth like planet. Searching this system is extraordinarily difficult because the stars themselves are so close together in our sky. Their brightness can overwhelm the faint signal of a small planet, making detection a problem of separating delicate motion from powerful stellar light. Astronomers have developed increasingly precise techniques for this task. Some searches examine tiny changes in a star's motion, while others look for the subtle dimming caused when a planet crosses in front of its star. So far, the planetary inventory remains uncertain. That uncertainty has not reduced interest in the system, it has done the opposite. Alpha Centauri is close enough to become one of the most important targets for future planetary studies, and proposed missions have even imagined sending tiny spacecraft toward it. The Breakthrough Starshot Initiative, for example, has explored the possibility of accelerating miniature probes using powerful laser beams. Such spacecraft would travel far faster than today's conventional probes, potentially reaching the system within a human lifetime. But the significance of Alpha Centauri extends beyond any future mission. Its two sun-like stars remind us that stellar neighborhoods are not uniform. Nearby space contains different kinds of stars, different magnetic behaviors, and potentially very different environments for planets. For you, the distinction changes the picture. The nearest stars are not all hostile. Some resemble the star that made Earth possible. Proxima remains the dramatic neighbor, but Alpha Centauri A and B offer another possibility, one where a planet might receive energy from a comparatively stable stellar source. That possibility remains unconfirmed. And yet, among the nearest stars, it is an important reminder that habitability may depend as much on the character of a star as the planet itself. The chemistry of life may be larger than the chemistry we know. Every example we have comes from one planet, shaped by one history. That gives us a remarkable laboratory, but a very small sample. On Earth, organisms survive conditions once considered impossible. Some microbes endure intense radiation, extreme acidity, crushing pressure, or temperatures that would destroy most familiar biology. Others live deep beneath the surface, where sunlight never reaches and energy comes from chemical reactions instead. These discoveries have changed the boundaries of habitability. For planets orbiting red dwarfs, that distinction matters. Surface conditions may become difficult during powerful stellar events, while underground environments could remain far more protected. A planet with liquid water beneath rock might, therefore, offer a refuge that telescopes cannot easily see. Astrobiologists have also considered whether life could emerge with chemistry unlike terrestrial biology. Our own organisms rely on ribonucleic acid, proteins, and water, all working within a narrow network of chemical processes. Another world might take a different route. Perhaps its biology would use different molecules to store information. Perhaps its energy systems would operate without oxygen. Perhaps radiation that damages terrestrial cells could become part of an unfamiliar biological strategy. These possibilities remain speculative. We have no confirmed evidence for such alternative life anywhere beyond Earth. Still, the idea changes how we interpret observations, because a planet lacking our preferred signatures would not necessarily be lifeless. Imagine searching an atmosphere for gases produced by familiar biology. We could examine the spectrum repeatedly, finding none of the combinations we expected. The planet might appear barren simply because our instruments are looking for the wrong chemistry. That is a genuine limitation. Our search methods are built around what evolution has already shown us. They are extraordinarily sophisticated, yet they remain shaped by one example. There is another intriguing possibility around red dwarfs. Their extreme youth does not last forever. These stars can remain active for long periods, gradually settling as their magnetic behavior changes with age. Since red dwarfs consume their nuclear fuel exceptionally slowly, their stable lifetimes can extend into trillions of years. That timescale is almost impossible to picture. The universe itself is only about 13.8 billion years old. A red dwarf can remain on the main sequence for vastly longer, continuing to shine after stars like our Sun have exhausted their ordinary stellar lifetimes. So the most difficult stars for life today may become something different over cosmic time. A planet that is inhospitable during its star's violent youth could eventually inherit a much calmer environment. If life begins after that transition, its entire history would unfold under conditions unlike anything experienced on Earth. We are accustomed to thinking of habitability as a narrow window. Around red dwarfs, it may be a moving target. And somewhere in the immense future of the galaxy, there could be worlds whose biological histories have barely begun, waiting for their stars to settle before the first chemistry capable of becoming life ever takes hold. The most familiar star in our sky becomes stranger when we compare it with its neighbors. Our Sun belongs to a relatively uncommon stellar class, and its long history has given Earth an unusual degree of stability. Every morning, sunlight reaches the surface, seasons follow their cycles, and the atmosphere remains capable of sheltering complex chemistry. That stability has layers. The Sun still produces flares and enormous eruptions of charged particles. Its magnetic field reverses over an approximately 11-year cycle, and periods of heightened activity can disturb satellites, radio signals, and electrical systems on Earth. Yet the pattern remains comparatively restrained. For our planet, distance matters enormously. Earth circles the Sun at about 93 million miles, giving its atmosphere and magnetic field room to absorb and deflect much of the star's energy before it reaches the ground. Those protections were built over immense spans of time. The magnetic field generated within Earth's outer core shields the planet from much of the charged particle flow arriving from the Sun. Above us, the ozone layer absorbs much of the most damaging ultraviolet radiation before it reaches living tissue. Neither protection exists in isolation. Earth's atmosphere, oceans, geology, and magnetic environment interact with sunlight continuously. Over billions of years, those systems have allowed life to move from simple chemistry toward increasingly complex forms, eventually producing organisms capable of asking questions about the star that sustains them. We rarely notice how specific that arrangement is. Move the planet closer, and temperatures rise. Move it farther away, and surface water can become difficult to maintain. Change the character of the star, and the radiation environment changes with it. Around many red dwarfs, planets must contend with a very different stellar rhythm. Their stars can release powerful bursts, while the planets orbit much closer to them, placing atmospheric protection under greater pressure. Our Sun gives Earth something more subtle: time. Time for oceans to circulate, time for continents to shift, time for chemistry to become biology, and biology to become increasingly intricate. The remarkable part is not that the Sun never changes. It does. The remarkable part is that its changes have remained compatible with life for so long. You can look upward on an ordinary day and see a star that seems almost inevitable. But nothing about this particular arrangement was guaranteed. Our world occupies one orbit around one star, inside one small region of one galaxy. The conditions happen to persist long enough for us to appear and recognize them. That may be the deepest lesson hidden in the familiar light above us. We call the sun ordinary because it has always been there. Across the galaxy, however, its particular combination of stability, activity, age, and planetary distance may be far less common than the sky suggests. Right now, somewhere beyond the darkness between stars, Proxima Centauri is changing. A flare may be rising from its surface at this very moment, sending energy outward across space. We would have no way to know yet. The information is still traveling. Proxima Centauri lies about 4.2 light years from Earth, so every view we receive is delayed by more than 4 years. The star we see tonight is therefore a record of what happened years ago. That delay becomes stranger when we compare neighboring stars. Barnard's star is roughly 6 light years away. Wolf 359 is about 7.9 light years distant. Light from each arrives carrying a different timestamp, although our eyes place those stars together in one sky. Consider the observations made of Wolf 359. Astronomers recorded 18 X-ray flares during a window lasting 3.5 days. Those eruptions had already happened nearly 8 years before scientists on Earth received the evidence. You can look at a star tonight and witness an event that ended years ago. The same principle applies to everything we have learned about stellar violence. A flare recorded by a telescope is never happening at the exact moment we observe it. The signal has crossed the distance between star and Earth first, carrying information from an earlier state. This creates a peculiar relationship between observation and reality. We never see a distant star as it is now. We see the version whose light has finally reached us. For nearby stars, the delay is measured in years. Across the galaxy, it can stretch much farther, allowing astronomers to study different moments in cosmic history within the same field of view. A single night can therefore contain many different times at once. The star beside another star may be showing us an older chapter of its activity. A more distant system can reveal an even earlier stage. Nothing about the arrangement is synchronized, even though our view makes it appear that way. There is something useful in remembering this when we consider planets around these stars. Their environments are changing continuously, whether we can observe those changes yet or not. A planet may be enduring a flare whose light has not reached Earth. Another may have already passed through an event we will not detect for years. Our instruments are always catching up. Even the most recent data carries history. The night sky is therefore less like a photograph than a collection of delayed messages. Each photon crossing the darkness preserves information about where it came from, when it left, and what was happening then. We receive those messages one by one. Meanwhile, the universe continues without waiting for our instruments. Stars flare, planets turn, atmospheres respond, and radiation travels onward. Somewhere near us, another event is already unfolding. We simply have not seen it yet. Time becomes almost physical when we compare a human lifetime with a star. Earth is about 4.5 billion years old. Complex animal life appeared much later, roughly 540 million years ago. Human civilization occupies only a tiny fraction of that history, perhaps 10,000 years. Against those numbers, the lifetimes of red dwarfs become difficult to imagine. Barnard's star is already more than 10 billion years old, yet it can continue fusing hydrogen for trillions of years. That is longer than our entire planetary history many times over. The red dwarfs around us belong to a stellar population built for extraordinary endurance. They consume their fuel slowly, allowing them to remain active long after stars, like our Sun, have completed their ordinary lives. UV Ceti will still be shining when the Sun has changed beyond recognition. Its future stretches across intervals so vast that familiar measures of history begin to lose meaning. Consider what that means for life. If biology ever emerges around one of these stars, its story could unfold on a timescale almost completely detached from ours. Civilizations could rise and disappear. Continents could rearrange themselves. Entire planetary ecosystems could transform while the same small star continues burning overhead. We are living during only one moment. The universe itself is roughly 13.8 billion years old, which sounds immense until we place it beside the possible lifetimes of the smallest stars. Red dwarfs may continue shining for trillions of years, making the present cosmic era resemble an early chapter. Their present activity may also belong to that early chapter. Young red dwarfs can be especially active, with strong magnetic fields and frequent energetic outbursts. As these stars age, their rotation gradually slows, changing the magnetic processes that drive their activity. Over enormous spans of time, the stellar environment can therefore evolve. A planet orbiting one of these stars may experience conditions very different from those present when its star was young. An atmosphere damaged early could potentially persist, recover, or be replaced through geological processes, depending on the planet's composition and internal activity. The important point is the duration. A world has immense time available to change. We tend to imagine habitability as something that either exists or does not. Stellar evolution suggests something more complicated. A planet can pass through different environments as its star ages, with opportunities opening and closing across intervals far longer than human history. Perhaps some worlds are being tested by their stars today. Others may already be entering a gentler era. Still, the deepest timescale belongs to the stars themselves. Long after humanity has vanished, red dwarfs could remain among the most persistent sources of light in the galaxy. Their future is measured in trillions of years. Ours is measured in generations. And somewhere between those two scales lies the possibility that life has far more time to begin, adapt, and endure than we have ever allowed ourselves to imagine. The nearest stars have given us something more valuable than a catalog of dangers. They have given us a way to measure how unusual our own circumstances may be. Across this neighborhood, stars follow the same physical laws. Their magnetic fields twist, their surfaces erupt, and their radiation crosses the space between worlds. None of it requires intention. Stellar physics simply unfolds. Yet life requires a remarkable sequence of conditions to persist. A planet must retain the materials from which chemistry can build complexity. Its surface or interior must provide environments where those reactions can continue. Energy must be available, but not so destructive that every fragile structure is repeatedly erased. Somewhere within those boundaries, chemistry can become biology. We know only one example. That limitation matters. Every idea about habitability begins with Earth because Earth is the only world where we have confirmed life. When we describe a planet as promising, we are comparing it against one known outcome, not against every possible form existence might take. Our stellar neighborhood makes that distinction especially important. The most common stars are small red dwarfs, yet their planets can experience conditions unlike anything in our own system. Their radiation changes the chemistry of atmospheres. Their magnetic activity can alter planetary environments. Their long lifetimes create opportunities on scales that human history cannot meaningfully represent. Meanwhile, Our sun occupies a different kind of stellar setting. Its behavior has allowed Earth's atmosphere, oceans, geology, and chemistry to interact across immense stretches of time. The result is not simply a habitable planet, it is a planet where habitability persisted long enough for complexity to accumulate. That distinction is easy to overlook. You and I experience Earth's stability as ordinary because every moment of our lives occurs inside it. We wake beneath an atmosphere that usually remains breathable. We move through temperatures that permit liquid water. We build cities without calculating whether the star above us might erase the conditions that support them tomorrow. Those assumptions are inherited from our environment. They are not universal laws. Perhaps this is what our neighborhood tells us about existence. Life may depend less on abundance than on persistence. A galaxy can contain hundreds of billions of stars and countless planets, yet the crucial question may be how many worlds remain suitable for long enough. Time becomes part of habitability. So does restraint. A star does not need to be perfectly calm. A planet does not need to be protected from every disturbance. What matters may be the balance between disruption and recovery, between energy arriving and complex systems enduring. Earth has lived within that balance for billions of years. We are one result of it. And when you look toward the nearest stars, you are seeing many other possibilities governed by the same physics. Some may be too harsh, some may be changing. Others may contain environments we have not yet learned to recognize. Our corner of the galaxy offers no guarantee that life is common. It offers something more precise, a single example showing that, under the right conditions, matter can become chemistry, chemistry can become life, and life can eventually become aware enough to wonder where it came from. There is a strange intimacy in discovering what exists beyond your own horizon. The stars above us remain distant, yet their physical reality can change the meaning of everything familiar. Within 9 light-years of Earth, several stellar systems reveal how varied our neighborhood can be. Proxima Centauri, Barnard's star, Wolf 359, and UV Ceti are all too faint for unaided human eyes. Their light reaches us through immense stretches of space, carrying evidence of magnetic activity, stellar eruptions, and changing environments around worlds we cannot yet examine directly. From your window, they leave no obvious trace. That is what makes astronomy different from ordinary observation. We can stand beneath the same sky that our ancestors saw, while knowing that events are unfolding around those distant stars at this very moment. A flare may be crossing interstellar space. An atmosphere may be responding to radiation. A planet may be losing particles from its upper layers. Somewhere, chemistry may be continuing under conditions unlike anything found on Earth. We simply cannot see most of it. The darkness between the stars is therefore filled with information, even when our eyes receive almost none of it. Telescopes collect wavelengths that human vision cannot detect, turning faint signals into measurements of temperature, magnetic activity, chemical composition, and stellar motion. Each measurement adds another layer to the same neighborhood. Proxima Centauri becomes more than a nearby point of light. Barnard's star becomes a physical system with its own age and activity. Wolf 359 becomes a source whose bursts can be reconstructed from radiation that began its journey years before reaching Earth. The sky does not change when we learn these things. Our description of it does. A familiar constellation can become a collection of immense furnaces, distant planets, magnetic fields, and radiation moving through space. What looked simple becomes layered, and what seemed permanent becomes a record of processes unfolding across different times. You can still look upward and see stars. Now, you also know that everyone carries a physical history. This is one of the gifts of science. It does not need to make the universe smaller to make it understandable. Instead, it gives us better questions and more precise ways to place ourselves within something far larger than human experience. Our nearest stellar neighbors are not merely points surrounding the Sun, they are natural experiments, each showing us another way that a star can shape the space around it. Some environments may be hostile to life, others may be more forgiving. Some worlds may have atmospheres, others may have lost them long ago. We do not yet know enough to assign every possibility its place. But uncertainty itself has structure. It tells us where observation ends and discovery begins. And when you return to the ordinary world beneath this enormous sky, the stars have not become different. We have simply learned to see more of what was already there. If you could place every nearby star on a single map, one fact would stand apart. The star beneath our lives would still seem ordinary, almost familiar, while the others would reveal how differently stellar neighborhoods can behave. Proxima Centauri is close, Barnard's star is close, Wolf 359 and UV Ceti are close, yet none of them provides the conditions we know Earth has maintained for billions of years. Their existence reminds us that being near a star tells us almost nothing about whether its planets can remain hospitable. The Sun gives us something more subtle. It provides a steady source of energy across the enormous interval in which Earth's atmosphere, oceans, geology, and biology have interacted. Its magnetic activity can become intense, but the long-term environment around Earth has remained compatible with complex life. That compatibility is the foundation beneath every question we have asked. You are part of the result. The light entering your eyes began at the Sun. The warmth reaching your skin began there too. Plants convert its energy into chemical bonds, while ecosystems build themselves around the cycles that follow. Even our technology ultimately depends on energy that arrived from this star or from ancient sunlight stored within Earth's materials. None of this makes the Sun the greatest star. It makes the Sun our reference point. We use it to define what a habitable environment looks like because it is the only stellar system we know from the inside. Every exoplanet, every atmosphere, and every distant flare is compared against knowledge gathered here. That changes the meaning of the nearby stars. They are not simply threats surrounding a fortunate planet. They are comparisons. Each one shows us a different relationship between a star and the space around it, helping us understand which conditions may matter for life and which may be less important than we once assumed. Perhaps another world has already found its own version of stability. Perhaps its star behaves differently, its atmosphere circulates differently, or its biology occupies places we would never think to search. We have no evidence yet that such a world exists, and science has to leave that distinction intact. Still, the question remains possible because Earth endured long enough for questioning minds to appear. That may be the most unusual feature of our stellar neighborhood. A star does not need to be exceptional in every way. A planet does not need perfect protection. What seems to matter is that enough favorable conditions persist long enough for complexity to continue building upon itself. We happened to inherit that interval. Now we can look outward and recognize how extraordinary an ordinary sky can be. The nearest stars continue doing what stars do. Their radiation crosses the darkness. Their magnetic fields evolve, and their planets, if they have them, continue through histories we cannot yet read. Above all of this, the Sun remains our local source of light. Because of it, we are here to notice the difference.